Okay, this lesson we're going to be looking at rational transformations. Remember, rational means fraction. So if you recall on 9.1, when we were looking at 9.1, we had rational when we were dealing with the inversely. So a rational function takes the form of p of x over q of x. So it's a fraction where p of x and q of x are polynomial functions, and q of x cannot equal 0. The reason for that is because you can't ever divide by a 0. So basically, rational functions have variables in the denominator. So make sure you have a variable in the denominator that's considered a rational function. So each piece of the rational function is called a branch. So notice here, there's a piece here and a piece here, which would be 2 branches. A rational function may have vertical or horizontal asymptotes, which we've talked about briefly whenever we went over this in Unit 1. So notice here that these two lines are approaching x equals 0, that straight line. That's an asymptote there. So an asymptote is when is a line that the graph is approaching but does not reach. Okay, so simple rational functions are represented by the parent function, f of x equals 1 over x, which is this graph here. So that's your parent function. So if we look at example 1, we're going to use the information provided to represent the function f of x equals 1 over x in multiple ways. So first I'm going to go to the table and we're going to plug in these values and see what we get. So I'm going to plug in a -3 for the x right there. That gives me -1/3. I'm going to plug in a -2. That would give me -1/2. Plugging in -1, that would give me a -1. Plugging in 0, remember we said we can't divide by 0. So that one is undefined, which is not on the graph. And then plugging in a 1, 1 divided by 1 is 1, 2 would be 1/2, 3 would be 1/3, because I'm plugging into this parent function right here. Okay, so let's plot the points to see what it looks like. So -3 at -1/3, -2, -1/2, -1, -1, and then 0 doesn't have 1, 1, 1, 2 1/2, and 3 1/3. So it's going to look like this. It's going to approach. Remember, it can't reach 0 because that's undefined. So this is our rational parent function. So here's the equation. The function family is rational. The number of branches, there's 2 pieces. There is no x-intercepts. The vertical asymptote, notice that this graph is approaching x equals 0. The horizontal asymptote, notice it is approaching y equals 0. So vertical is always x equals a number. Horizontal is always y equals a number. So there's 2 asymptotes here on this rational parent function. So the domain we're going to write, there's 3 different ways of writing it. I don't care which way you write it, but I'm going to go over each way. So if you look at the domain, for inequality notation, the domain looking at x is everything except 0. So x can be less than 0 or x can be greater than 0. So you'll have 2 pieces to that because you can't have a 0 there. Interval notation, you can go from -infinity to 0, but it won't include 0. And then union, remember, is like an OR statement from 0 to positive infinity. So again, it's not including those zeros because I don't have brackets there. Set notation, if you remember set notation, you use your curly bracket. You have the set of all x's, so you have just a straight line. It's all real numbers except 0. So you would just write x cannot equal 0 because there's no way of listing all of those out except 0. So there's your domain for this one. Your range, looking at the y, it's very similar. So y is less than 0 or y is greater than 0. It can't equal 0. Same thing for the interval. And then the set of all y's are all real numbers except 0. So y cannot equal 0. Okay, so again, I don't care which way you write your domain and range. We're not going to do the next part, so let's flip over. back over at the front, notice that this is what we're going to be using. Notice that your asymptotes, your vertical and horizontal of this rational intersect at the origin. To use these values here. So from -2 to 2. So I like to use those points. Okay, transformating. So the transformations that we've already discussed with all the different functions that we've talked about is very similar. So looking on your rational function, a reflection about the x-axis occurs with a negative a or b. So the negative can be on top or on bottom, and that's a reflection over the x-axis. A vertical stretch or a compression is the absolute value of a, which means just the positive version. So if you look at a is going to be the vertical stretch or compression. And then your horizontal stretch or compression is based on your B, so that's vertical. And then your translation horizontally is your C. So inside parentheses, if there's a minus, remember it's always the opposite. Also, notice here it says the vertical asymptote is always x equals C. So the opposite of what you're showing in there, that will be your vertical asymptote. And then the vertical translation is your D on the outside of the fraction. And then also your horizontal asymptote would be y equals D. Okay, so let's look here. We're going to start with our parent function. We're going to go to the new function, -1 over x plus 3 plus 2. So I think the easiest way to do this is to write your verbal description first. So the negative symbol will reflect it over the x-axis. And then your x plus 3 in the denominator will go opposite. So it'll go left 3. And then the plus 2 on the outside will go up 2. Now, so keep that in mind. So what we're going to do here in order to find our new function is we're going to go ahead and shift it. So normally it's at the origin where they intersect. I'm going to shift it left 3, 1, 2, 3, and up 2, 1, 2. So left 3, up 2, I'm going to plot the point. It's not really a point, but I know that that's where my horizontal and my vertical asymptotes will intersect. So that's a great way of doing rational is translating your intersection of your vertical and horizontal asymptotes. So go ahead and draw those two dotted lines when you shift it. Now, whenever you are thinking back at your rational parent function, so let's start. Let's act like this is our new origin point. Normally I have a -2 and -1/2. But since there's a reflection over the x-axis, that would be a -2. So I'm going to go left 2 and then up 1/2. And then the next point on the front from our parent function was -1, -1. So normally I would go left 1, down 1, but I'm going to go left 1, up 1. And then the next point was the 0 didn't work. So then we have a +1. Normally that's 1. So I'm going to go right 1, but I have to do the opposite and go down 1, and then right 2, down 1/2. So that helps me with knowing what my rational function will look like. So again, I like to use those points. And then that will help you with your table here. So we did plotting your points. Now look at the actual points. So that's 1, 2, 3, 4, 5. That's -5. And then up 1, 2, 2.5. And then we plotted the point -4, 1, 2, 3. And then we plotted -2, 1, and -1, 1.5. So those are the points that we found from the parent function. So again, it's easier if you're just plotting the points and then you can look at them and figure out what they would be. Okay, so vertical asymptotes. So the vertical one, look at the vertical one. This one's vertical. It crosses, remember it's always x equals, it crosses the x at 1 to -3. And then the horizontal one crosses the y at 2, notice it corresponds with your shift. If it goes left, it's going to -3 on the x. If it goes up, it's going to +2 on the y. So that will help you also with your asymptotes. So we want to find the domain and range. It does not matter which one or which domain and range that you use or notation. So your choice. So the domain of f is just from the front. So I'm just going to use interval notation because I think it's the easiest, but you're welcome to do whatever. So -infinity to 0 was the original, and then 0 to infinity. Now let's look at our g, which we graphed. This is our new one. So notice our x's cannot equal -3. So it goes from -infinity to 3, it stops. And then from 3 to +infinity. It should be negative. Okay, so then looking at our range of f, that was the front, -infinity to 0, and then 0 to infinity. The range would be, notice your y stops at 2, equals 2, so -infinity to 2, and then 2 to infinity. So again, your asymptotes will help you with finding your domain and your range. They should correspond together. All right, next section, we are going to write the equation for g is obtained from translating from the parent function 1 over x. We're going to write a verbal description, and then if you want, you're welcome to use a graphing calculator to verify your answer. So the top is your a, that's vertical stretch. So vertical stretch by 4. And the denominator is x minus 2, so that's going to go right 2. And then the -3 on the outside of the fraction goes down 5. Okay, so b, whatever number is on the bottom, remember that's the horizontal. And since it's a 2, you remember do the reciprocal, so it's always the opposite. So horizontal compression of 1/2. And then there's nothing else, and then we have a +3 after the fraction, so that would go up 3. Okay, so C, the negative is a reflection over the x-axis. The 3 on the top is a vertical stretch by 3. And then in the denominator is x plus 1, so the opposite would be left 1, and then the -2 after the fraction would shift it down 2. All right, last part, we're going to write the equation of the function. We're given the transformations this time, so we're going to come up with function g. So it's going to be reflected over the x-axis, so that puts a negative. It's going to have a vertical stretch by 2, so that just puts the number in the top. And then it's going to go right 5. So in the denominator with your x, you need an x minus 5. There's no vertical stretch, or there's no vertical translation up or down, so we don't need anything after the fraction. Okay, so this is transformations on a rational function. If you have any questions, please let me know.